Hello, good evening everyone. This is week 5 and this is a tutorial for stochastic control and communication. I'm Apurva, I'm a PhD student at IIT Bombay and I'll be taking this tutorial session. Okay, so let's take a recap of what was covered in the last week, and after that we will come back to what is to be covered in this week. Okay, so last week we talked about the DP algorithm. We applied it to a problem. We first saw what was the DP algorithm and then we applied it to a problem and see uh, how it is to be handled. So we said, okay, this is a good picture of what the algorithm ultimately talks about. This talks about the principle of optimality. The DP algorithm does a kind of a backward induction. It starts at the very last step, chooses what is the best option there. There is no action at the last point, so it goes one step before and then says from the second last step what are the best options possible. Choose those, keep those in mind, go one step back, and the process continues. In a more formal setting, it looks like the following. This is the problem that we are trying to solve, which is to find the minimum cost, find the minimum expected cost with respect to policy u1, u2, mu1, mu2 till mu n minus 1, and we want to minimize the expected cost. This is the terminal cost, this is the stage wise cost, where this xk are the states, uk are the steps, actions taken at that time or at that step k, and omega k are the randomness, source of randomness in the problem. This is if we are taking the stochastic control view of the problem. So the algorithm says that we are supposed to look at the terminal step, go one step backward at a time. So if we take this k to be n minus 1, then this k depends on the stage wise cost at that point, and we are minimizing for the actions at that point, and we take whatever was the terminal cost from the previous step, and we keep doing that backwards, and hence this is what we are supposed to solve for. Whatever this jk of xk is at the time kk, it is optimal. And once we have done this, once we have reached the very last stage, or whether it is k equal to 1 or k equal to 0, however we've defined the problem, currently we've defined it for k equal to 1, that's when we have managed to find out all these optimal decision rules. So we have the optimal policy by the time we've reached here. In the mean steps, we would have found the optimal up till that point. So starting from n minus 1 till k is when we would have found optimal policy up till the kth intermediate step. Okay, so this is the core algorithm. Then we saw how it can be applied. We skipped the proof. We applied it to the inventory control problem. Inventory control problem had a linear dynamics of this kind. And in the process of applying it to this problem, we saw that the application is just recursively backwards. We took the example of the scenario where backlogging is allowed, and we saw that that's a difficult one to solve because it has infinite state space. X can go till minus infinity. So rather we focused on the one without backlogging. This was the one that was taken in the class also. This is the kind of setup that you would see in problems also. Then we said, okay, let there be another constraint between xk and uk, and with that what are the values of xk possible, and correspondingly what are the possible actions that can be taken. Then we applied dp and solved and found out what is the optimal action and the optimal value for each action, each state. We went on, we did this for the whole thing. Then we tried to compare the stochastic control view with the MDP view. MDP view basically said that we have a policy we have something that is called as the Bellman equation, or the value function v of pi for a particular policy pi, which is just the expected rewards starting from time k equal to 1 till time n minus 1 plus the terminal reward. Suppose we are assuming that we start from a state S. So, and this is to be done where the action AK is based on policy pi. So yeah, this way. Similar to the DP algorithm we saw in stochastic control, what we get here is what is called policy iteration. We did not prove this. This is something that you can try on your own if you're interested. This is more like the RL view of things. Here, it's the same idea, but this doesn't need to be done again and again. It's not dependent on time steps now. This gives us a recursive equation. This side depends on the value function. This side also depends on the value function, and we're supposed to be maximizing with respect to the different actions that can be taken. So we saw this. We applied this to an MDP and saw that a very simple MDP also requires a bit of effort to solve and find the optimal actions and the optimal value function. This is what we had last time. Today we are going to talk about another example, which is the optimal stopping problem. And after that we'll go to another class of problems called linear quadratic problems. So let's get started with this optimal stopping problem. This is the focus for today. Okay, so this is we are back at week 5. This is a recap, so I'm going to skip this recap. We already know these things. So this is J, the object that we are trying to optimize, the original problem. The original problem basically is interested in optimizing the expected cost. That has the first step, which is the terminal cost, and then the next part has the stage. Let's say stage is starting from 0 till n minus 1, and this is gk of xk, uk, and some omega k. The DP algorithm basically says that what are we supposed to do? We are supposed to take this jn value at the last terminal point for all the states xn. So this is for all the states xn that are feasible. So this is basically just gn of xn, nothing else. For k less than n minus 1, for any other time step before that, we are supposed to look at the following object. We are supposed to do it one step at a time. So see here, the optimization was for all the policies, for all the decision rules, all of them, all the strategies. Now we're doing one at a time, and we have shown this last time that this object and whatever we get from the whole process ends up being the same optimal value, and it gives the same policy. So this is the stage-wise cost at the time step k plus whatever we had, whatever is the optimal that we had from the previous time step, taken at xk plus 1 at the previously considered state. And we know that this can be actually simplified to write this is jk plus 1 of. Now we know how this comes from a dynamics, so that let's assume that dynamics is some fk. This is jk plus 1 of fk acting on these objects, all of them. So xk, u, uk, and omega k, all of these things. What this means is from the salesman problem, traveling salesman problem, this is the example of traveling salesman problem, famously called as just TSP, where the salesman has to go from point A to point B. What is the best path that he should be taking to go from point A to point B? Maybe he's trying to optimize the time, or maybe he's trying to optimize the distance. It can be written in either ways. So he should be doing it backwards. He should start from here, then look at the next time step. It can be time step or node wise. You can decide how it is done, and then look at that, go one step back, and then optimize the whole thing. That's the process. Now we're taking the example of optimal stopping problem. This is what we're going to focus on today. So this is just something that I've taken from the lecture notes as it is, and then I'll explain what all of these things mean. So consider what is called as an optimal stopping problem. So consider that there is a Markov chain with state space S dash. We are assuming that the space state is finite. That's what it means to say, and that the cardinality is less than infinity. Okay, and there is one more Markov chain that is uncontrolled. Uncontrolled just means that there are no actions to be taken. So there are no actions here. Now in the chain, this chain S dash, some actions are available. Those two actions are called to continue or to quit. As in, whatever is happening, whether to let that continue or you stop that process. Once you stop that process, something in the background continues, and you've basically transitioned from some state from S dash to some state in this uncontrolled Markov chain. Okay, so if you decide to continue, there is a cost at time t. If you decide to quit, then there is a reward at time t for stopping the process. And this process you can think of as something that continues over the time horizon, over finite time horizons. Okay, and there is a terminal reward given for this problem. S refers to some state at time, and in this case. So one of the examples mentioned in class to think of these stopping problems was an example from finance. So I'll try and elaborate on one such example from there. So suppose you've decided to enter into a stock. You've already entered. You've bought some number of stocks. Then you decide whether to stay in that stock given what you see about the market, the price fluctuations, or to exit. So that sort of brings us to these actions that are available to you. Whether you continue staying in the stock, meaning hold the stock in the finance language, or to exit and hopefully book a profit or book a loss if for whatever reason you have no choice but to. Okay, so in such a scenario, whatever price fluctuations are happening in the stock, that can be imagined as a Markov chain. What price is going to happen next depends on the previous time step, exactly where the price was last. And well, there are other factors in this which are not captured directly, but they're there, which cannot be controlled by users who are buying these stocks. But there are other factors that affect the market. Okay, then if suppose there is a stock that is going however it is going, and at some point let's say this is how the stock is going. Let's say you entered here. This is your entering location. Okay, and then you decided to exit here. So your entering could be labeled as your starting state, and your exit could be the price at the new state. So what will matter to you is whatever this difference is from here till here, right? This will decide whether you are getting a reward if you've decided to quit, or if you've not decided to quit, what exactly is happening. Suppose you did not decide to quit here and you let it continue, it went till here, and after that, for some strange reason that you didn't know about, it fell, and it fell up till here. It was a sudden fall, nothing could be done. So now what happened? Since you decided to stay in the stock, you did not exit here, you stayed in the stock, you saw all of these fluctuations happen. You chose to take the action of continue, not quit. Then for staying here, what exactly have you lost? You could have made a profit here, but you didn't, because you didn't make those profit. There might be a cost to you that you've just let your money stay there. It's like saying you could have earned some profit on that money if you had put it elsewhere, and since you didn't, you paid a cost, or maybe you had to pay a cost, extra brokerage cost, to enter that stock. This could have been also thought about for options as well. Another way to think about this could be, if suppose what you're doing when you're trading and so on, you're doing intraday, so you're doing it on a daily basis. So if you decide to not exit at the end of the day, whatever is the value, suppose the value at the end of the day is here, this is the price that you'll get, and this price, this is the difference you'll get, that's okay. But at the same time, because you did not exit yourself, there will be a penalty imposed on you, so that can be thought of as this penalty. And clearly this is something that could potentially depend on S, and whatever S dash you were forced to exit at, so whatever is the next state that you landed upon. So this is a more refined example in that sense, but it still captures the things that are happening, and the strategy that you could create for whether to hold, whether to not to hold, if it can be modeled into this, would be like an exit strategy, and that can be thought of as an optimal stopping problem. Okay, terminal reward can also be again thought of as what happens at the end of it. Suppose you need to exit at certain point of time. This is typically something that happens in options trading, that you have an expiry of whatever you've bought, and if you don't exit, then there's a terminal something reward. It's typically a penalty, it's a huge penalty, but sometimes you can think of it as a reward, and it's fine. Okay, so this is a good example of how this idea of optimal stopping problem can be applied to an actual real life situation. So the one that I've described is called exit strategy type stock market example. So this is an example from finance. You could have also taken the example of options here. So that's another branch that you could have taken. Similar thing, you're just coming up with exit strategy, whether to hold or not to hold. That's roughly just the idea. Okay, now let's define all of these things a bit more formally. So we know an MDP requires a state space, corresponding action space, rather it's the union for all states in the state space. Then there is a time horizon. Then there is a reward system, a reward mechanism for all the states and actions in next states. There is also a probability distribution, or the transition probability. Like what are the chances that you'll go from this state to this state, given so and so action has been taken and you're starting from so and so state. So let's formalize all of these things for the core problem. So let's say we are doing this for time steps starting from 0 till n-1. The state space is what we are referring to as S dash, the core Markov chain, or as per our example, the price fluctuations in the market of a particular stock. And the state space needs to also have the other state. Like suppose you exited the market at some point of time. You have exited, but that doesn't mean the stock price fluctuation stopped. You no longer have any action worth taking because you're already out of it. Let's say the actions that you have available are continue or hold, continue or exit. So at this point, you don't have another action available to you. So you're technically out of it. But that is also a state, or that's also a whole state space. That's where you enter. It needs to be included in your definition of MDP, otherwise there is a slight problem here. So this is the whole state space. Now, what kind of actions do you have available? If you are in the state space where you can take actions, then you have the option of either to continue or to quit. So you have two actions available. On the other hand, if you've already decided to quit and exit, then the way we have defined the problem, you don't have any other actions available. So you are technically just continuing. That's the only action available. That happens on its own. You have no control over that. Okay. Now the reward model that we have here is based on your current state and your action. If you were interested in RT of S, A, S dash, the next state, then you could do that also, and the way to connect these two would be just take an expectation of this with respect to the transition probability. Okay, so meaning you can connect these two to each other, but for that you need this. From here to go here, you'll have to sort of more than one option, then you can come up with various variations of how you want to do that. Alright, so let me focus on the version that we have. Now, what happens, what kind of reward or cost you get depends on the kind of action that you're taking. Suppose in the current state, you are in the part where something can actually be done. Then, if the action that you take is to continue, meaning you're staying in that Markov state, that means you will incur a cost. So this is minus CT of S that we saw earlier. That you'll incur a cost because you decided to stay, you decided to continue. But if you decide to quit, you will get a reward that depends on the time and that depends on the state. And let's say if you decide if you're in this, then you can decide what happens here. Maybe we can just take it to be 0 and it's okay. Okay, and Rn of this, let's say, is just some H of S for all the states that are technically feasible. Just a moment, I am verifying if I have written this appropriately. Okay, this is fine. Then next is to describe what is the transition probabilities. Now transition probabilities depend where you're at, where you're going, and what action it depends on. So if you are in the core Markov chain and you decide to continue, meaning you started from some state and you go on to some other state, or like as per the previous example, stock market, you were here, you started here and you've gone here and you've decided to continue, then what is the probability of this happening? What is the probability of you starting from here and going here? That's what it is capturing. Since it is in the scenario where action has already been taken, it's happening on its own, action does not play a role. So this can be written as pt of j given s. Okay. Now another scenario is, suppose you were in this state, you were a part of this, but you decided to quit. This is where it stops for you. That means the next state available to you is from this delta, because you decided to quit. Now, if that's what has happened, if your S and J are appropriately defined, that means the probability of this happening is 1. Because by taking the action of quit, you went from a state, from the moving Markov chain, to the one which is what is calling as the stopped state. Or you could have also had this if you were in that stop state and you continue taking the action, which is no action whatsoever. So this is with probability 1. Everything else will have a transition probability of 0. You can think of it this way. Everything else also includes things like, suppose you were from this state, you took the action equal to q, you decided to quit, but you're saying j still belongs to s dash. Now what exactly is this? That you started out from, you decided to quit, but you're saying you're still in the same state where you have the option of taking an action. This cannot happen. Hence, the probability of this would be 0. So this is an example of else. Okay, so this becomes our formal model that describes what is the optimal stopping problem. Okay, I described one example throughout, which is the example of stock market or the exit strategy in a stock market. Whether you're talking about a stock or you're talking about options, a similar idea holds in both of those examples. Another possibility is to think of an interview panel, what is called as the secretary problem. So now I'll go about describe this in a bit more detail. So suppose there are n candidates. Okay, there is only one candidate to be chosen. And the selection happens instantaneously. Either you are selected or you're not selected, and you're told that while you're in the interview. Meaning, from the perspective of the interview panel, they, based on the candidate that they see, they are supposed to decide whether to give the offer to this person or not. If they decide to give offer to someone, they don't look at any other candidates after him or after her. But if they decide to not give the offer to this candidate, they get to the next candidate. Okay, so this is another example of an optimal stopping problem. So let's look at it more carefully. Okay, now here the state space for us is very simple. We describe the state space as best candidate so far. Meaning, if I have total 10 candidates and currently I am at the 5th candidate, is 5th candidate the best candidate from the ones that I've seen so far or not? That is the only thing that is being captured in my state. So this is captured by 0 and 1. 1 would mean it's the best candidate. It's not the best candidate. The keyword here is so far. Let's say the actions available. Now the actions are available to the interviewers. Whether to give this person an offer. If the person is given an offer, then that's more like a quit state, as in the MDP sort of stops. Or you continue interviewing, meaning you go to the next candidate. Okay, and these actions are available for all the states. If you've already given an offer, else means if you've already given an offer, then there is nothing else to do. You can interview the other candidates, but you cannot give offers anymore, or you can just stop the interview process and be done with it. Okay, so now here in this example, we're saying that the cost is just 0. There is no cost for continuing, but there is a reward. Now let's look at what they're asking for and then look at an example and try and understand it better. So what they're saying is, if you ended up selecting a candidate who is not the best so far, meaning at time equal to t, one you've selected is not the best, then you get no reward. But if you selected someone who is best so far, your reward is the probability that the current candidate is the best amongst all. With that probability, that's what is your reward. Meaning, if you manage to get the best person, you'll get a high reward. If you didn't, then your reward will be dependent on that, and it'll also depend at what time step you are. So if suppose the best candidate is the last one, so okay, let's take the example more carefully and let's think about it. So let's say I have an interview panel of 10 candidates. The rank 1 is what I'm describing as best. Okay, so what I've written here are the ranks in and the order in which they are coming to the interview. So first rank comes first. If at the first stage he's already accepted, then the reward depends on what are the chances that this is the best so far. Well, no one has come before him, so this is what it is. But there are still a lot of other candidates to look at. So we need a probability of that. We need the probability that this can actually happen. With what probability it can happen. So we'll come to that. So another possibility of order in which the candidates can show up is the following. Asha, by the way, I could write these orderings in terms of our state. Our state could only be 0 and 1, right? So if I try writing that for this ordering, it would basically be, okay, let me write with a different color. I got the best one already, so that's 1. After that, I'm getting someone with the rank 2, meaning this one is definitely worse than this. So not the best so far. Best so far has already happened, so this is 0. And this will actually continue being 0 up till the 10th one. This is the first scenario. What if it's the opposite scenario? You get the worst one first. Then the states, so this is written in terms of states S at each time interval t. Okay, here I got whatever I got, so that's anyways the best one I could have gotten at that time. That's okay. Then I went to this person. Now between 10 and 9, 9 is better. So again, it's a 1. And it will keep being 1 till you're at the last one. So now the question is, how should you decide? Because as an interviewer, you only know the candidate that you see right now. Is this the best that there is? What if the first one that came is actually the best? But because you don't know what the pool is like, you decide to not accept that. And then you go to the next person. Then do you accept that or not? So this question is basically asking, what is the best strategy to give offers in a placement round when you need to give the offer right then and there? You can't go back. You can't look at the whole pool, then know and then decide and go. This is more like an online process of giving the offers. Okay, now let's take this example. This last example is what I'm referring to right now. Before we figure out what is the reward here, let's write down this in terms of S. So what is S here? I got the first candidate I got has a rank 5. Okay, that means that's anyways the best one. But after that I got somebody with a lower rank. So not the best, not the best, not the best, and this goes on till 10, not the best. After 10 I got 1, meaning this is actually the best candidate that there is. This is by default the best candidate so far, and this is actually the best candidate also. And then again it's 0, 0, 0. So now what they are saying is the reward is in the following way. The reward refers to what is the probability that the current candidate is the best candidate throughout. So the fact that it is the best candidate means the candidates here all the candidates before are arranged in some order. So this is just referring to the number of ways of arranging this is referring to time t, right? So this is RT of rank 1. S is what we are referring to. And time step t. So this is number of ways of arranging these candidates. In groups of t with best candidate at time t, divided by, well, all arrangements for t subgroup. So what exactly is that? That is, okay, we'll come back to this. That is, we know the current candidate is the best one, so that is fixed. So the remaining time steps for us are, the remaining total are n-1, and the remaining subgroups that we need to create are t-1. And this needs to be divided by all the variations that we could have had. So that is NCT. If you simplify this, this is n-1 choose t-1. This is n choose t. So we get t by n here. For our example, this is 7 by 10. So what is this meaning? This is the reward that I'm getting. Okay, so this is our formula for the reward, that is t by n. Now let's continue. Let's say for our problem we have terminal state in the following way. If you get the best candidate at the last time step, you have a reward of 1. You got the best candidate, so you should offer them. You got what you wanted. But if that's not what happens, your reward is 0. You let the whole process continue and did not find a good candidate. You did not find even a suboptimal candidate. Your last candidate is not that good, so you're stuck. You did not sort of end the process well. So then your reward is 0. This is the terminal reward. Now let's look at the probabilities. Remember, there were certain conditions here, there were certain conditions here. The main probability that we need to focus on is this one. Is this one. Probability of going from state J to S, where both J and S are in the main chain and the action is actually to continue. Now, what exactly is J and S? J and S is referring to candidate that you've seen so far. They're either 0 or 1. Best candidate so far. Now imagine the ranking that came up is the following. Okay, there are 10 candidates again. So I'm going with the previous example. There are 10 candidates. Let's say I'm looking at a snapshot of this time slot. The current candidate that I got is ranked 6th. The only thing that I know is next candidate will not have the same rank. It will have some other rank. Some categorization is done and same ranks are not given. Let's say that's how it is. Now whether the next one is a 7 is something with a higher rank or a lower rank does not depend on what this is. right? It can be any of them. It can be any candidate. So what next state I go to is independent of the current state, and that's exactly what this says. Okay, now let's see what this actually means. So what is this now asking for? What is the probability that your current state, your next state is J? Your next state is the best candidate so far, or is it not the best candidate so far? That's what these two mean. And it's the same idea as before. So if you do that, it is dividing it in t factorials versus t plus 1 factorial. So that gives you just 1 by t plus 1. Why did I do t factorial? I know I already got the best. I already got the, not the best, I already got the candidate which is better than the previous one. Best so far. If I didn't get that, the remaining would just be t divided by t plus 1. Notice here t is starting from 0 and going all the way till n minus 1. Okay, so we have the transition probabilities also. So for us, the next job is to actually apply dp to this problem and solve for the following. Okay, and to apply dp means we are looking at stage wise. Let's say at the terminal step, so at t equal to n, we are told what is happening at the terminal state, right? These are the terminal state cost. This is h of s equal to 0. We said that is 0, you get no reward. H of s equal to 1, you get full reward. That's exactly what has happened. This is anyways a good thing. See, if the last candidate is the best candidate so far, you actually managed to get the best candidate so far. So your reward should be the maximum reward that there is. If you stopped anywhere before that, you would not have gotten the best one, because in this example at least, the best one is the last candidate. So this is the maximum reward that is anyways possible. So the reward is between 0 and 1. That's the range of rewards. And if you decide to quit, then for the remaining, then there's nothing. So this is the stopping state, the different Markov chain that we're talking about. Okay, so what are you supposed to do for time steps less than n? You're supposed to maximize this object, expectation, the stage-wise cost. The stage-wise cost is ct of s plus rt of s plus whatever you have from the previous step, which is jt plus 1 of the previous step. So I am just gonna call it s dash. Previous step meaning actually time t plus 1. Notice these two have nothing to take the expectation over. This is for the current step. Okay, this is for the current state. This is the one that's not for the current state. This is for the next state. So the following can be written as, okay, right now I'm still writing it as the expectation is only over this part. And notice the expectation here basically means we're looking at the transition probabilities. So ultimately what we're looking at is p s dash given s dash is whatever is the next state possible, jt plus 1 of s dash. Okay, for the two actions. You could write it more carefully if you want, it's okay. Alright, so now let's go over this. What exactly is this object? So the two scenarios would be, if you suppose you decide to continue. If you decide to continue means that you will get a cost, but there won't be a reward. This reward is anyways only there if you decide to quit. So this is one thing, the stage-wise cost, and whatever is the expected reward that you get from here, because then you'll be within that region only. So you'll have something here. If you decide to quit, then that means the only thing that you're considering here is the next state is just j delta, j of delta. Then that's the part that you have to consider. So let's write it out carefully. The two are as follows. Suppose you decided to continue in the first scenario. So this is the stage-wise cost that's still there. This won't exist because there is no reward, because you're continuing. If you've decided to continue, there are two possibilities for this. Okay, let's not take it to be a specific yet. Let it be still for S only. So you will do ps dash of S. Okay, this is one side of it. This is if you decide to continue. If on the other hand you don't decide to continue and you quit, that means you have RT of this, and if you've decided to quit, the only state that you will get to is the delta state. Okay, and this is just one delta state. For the delta state we've just taken it to be one object, so this is just it, and jt plus 1 of that delta state is all you need. Okay, and you can talk about what happens for this for the two states, for s equal to 0 and s equal to 1. So let's write out those things. I might have to move a little bit, move these objects a little bit. Let's do that. So let's say the state that we are considering is s equal to 0. S equal to 0 means this gets fixed as 0, this gets fixed as 0. But hold on. Before we do that, we already know there is no cost. So this anyways goes away. All that we have is this object. This is still there, this is still there. This, we don't know what this object is, but yeah, we know that this is just 1. Why is it 1? Because we are talking about this scenario. Yeah, we are talking about this scenario. Choosing the action to quit, going from state S dash to a state from delta. If that is the case, then the probability of that happening is just 1. So let's write this for state s equal to 0. So s equal to 0 means s dash can take either of the options, right? jt plus 1 of 1 plus p0 of 0 jt plus 1 of 0. This is this object versus RT of S. RT of S is for RT of 0 plus this is 1. This is just JT plus 1 of delta. Okay, this is when the state is S equal to 0. Now let's similarly write for the other one, which is JT of 1, that is same object, but now this S is 1, so we get a probability transition from 1 to 1. JT plus 1 is 1, and this is probability transition from the current state 1 to the new state 0. JT plus 1 0. And this is RT of 1 plus JT plus 1 and delta. So remember, we know these probabilities, and also we know what these two are. But let's focus on this before we focus on the other objects. Before we can write that, let's just focus on these two. So to be able to focus on this, see, what is this? What have we written here? We have written JT for any S. The maximization is over the actions available. What are the actions available if you're in this state? The only action available is continue. That's the only action. So there's nothing much. So there's just one object. At that point, what do you have? You have a cost CT of S. Okay. And you have this object. That is the probability of going to some other state, starting from a state that is in delta. And let me write it as J actually. And JT plus 1 of J. Now J could be either JT, this could be any of the two. So this could be, 1 second. So this J could belong to S and delta. Okay, now let's look at this portion a bit more carefully. So if J belongs to delta, so this is, what is this? This is delta to delta. We know the probability of that is just 1. That means we get JT of delta. This is one scenario, right? The other scenario is if it is something from S. So this is, okay, J belonging to the running chain, which is, let's call it, okay, let's call it I. Okay, and minus CT of S is as it is. There's no maximization here. We're coming to the core logic, but let's still finish it. Now we know this object staying here is just 1. This object is 0. If you reached a stop state, you cannot go back to the core one and be able to take actions. It's like you exited the stock already. You will have to re-enter to be able to decide whether to hold or exit. So that actions are not available to you anymore. So this is not possible. So this will be 0. So we are left with these two things, minus CT of S plus, that's just 1, JT plus 1 and delta. Remember the way we have in our problem, this is already 0. The only thing that matters is what is the J at the previous time step. for delta, this is already 0. And remember, this is starting from time step n. At n, this is 0. That means for n minus 1, also this will be 0. And you can just continue and it will be 0 for all t. That means what happened here is jt of delta is 0. So with this argument, I can go back up, and using this argument, I can cancel these two objects. This just is 0. This is also 0. Okay. And now what I can do is, to complete the whole process, I can write down what these probabilities are. And remember, these probabilities did not depend on the previous state, so I can simplify them even more. It's the same things that is going to be there both the time. So probability for 1 is okay, I made a slight error here. This should be something that depends on t. Yeah, sure, here it won't matter. That part of the argument does not change. So when we're talking about the state 1, this is just pt of 1, and pt of 1 is 1 by t plus 1. So if I write that out properly, I will get okay, one more thing. What is RT of 0 and what is RT of 1? Okay. RT of 1 is this, t by n. But RT of 0 is 0. No reward if you're choosing someone who's not the best so far. So this is also 0. No, sorry. This is also 0. Okay, so let's write what was RT of 1, that was t by n, versus for the other one, this object is exactly the same, comma 0. Now notice these j's, there is nothing that makes them negative. The cost is anyways not there. The terminals starting are between 0 and 1, are 0 and 1 exactly. So everything is going to stay positive. That means the max of these two will be exactly 0 or this. That means we could just say that this is because this one will always be greater than or equal to 0. If both of them are 0, then you can choose either action, it's fine. But if this is greater, then this is the one that you should be choosing, and that's what this means. Which in return means this is the action for continuing, this is the action for quitting. Which means it's better to continue if the candidate that you see is not the best so far at any time step. What happens to the other scenario? If the candidate that you see right now is the best so far at a time t, what should you do? You should be comparing this with this. Now this can just be called as jt of 0, and that needs to be compared with t by n. Now this gives you a few scenarios, and that tells you what you should be doing. So let's look at those scenarios. If your t by n is greater, then it's better to quit. If your t by n is greater than this, whatever this value is. If your t by n is less than this, then it's better to continue. If they're equal, then you can do whatever you want. That means you're roughly getting an optimal policy out of here already. So let's look at this policy again. If S, so this is telling you if you are at a time before some precise time such that this condition is still not satisfied, you're at such a time that this is not satisfied because both of these are getting affected, then what should you do? And if you have reached that time and you're beyond that threshold time, then what you should do? So nothing changes for this part. Here you should just always continue, meaning if you have not seen the best candidate so far, you should not stop, you should continue, you should wait for the best candidate. If you do see the best candidate but you're seeing that candidate before a certain time, then it's actually better to continue. But if it's the opposite, if the time has a certain time has passed and then you're seeing the best candidate, you should just select that candidate and stop the process. So this is the optimal time. And at that optimal stopping time, this is the policy that should be chosen in the kind of game that we're talking about, in the kind of problem that we're talking about. If you do that for all the time steps, this would become an optimal policy. Now, in the lectures, something was proven as to why this is the optimal policy and what this policy means. What is this optimal stopping time? So I'll not go through the proof, but I'll just point out what was the core idea. Yeah, so the optimal stopping time, like the max t such that this happens, jt of 0 is greater than t by n. If this happens, then you should choose the best candidate that you get at the next moment. This is telling you that roughly this time happens after you've seen something like 36% of the candidates. See, that depends on n. N is the number of candidates. So after you've seen some pool of the candidate, then you have an idea what to expect from the whole pool, and after that, whoever is the best candidate that you get, you should choose that person. This way you'll be able to optimize the reward that you're trying to optimize in this process. Okay, now there are a few variations to this problem that can be thought of. Difficult to do, but there are certain variations to this problem, so I'll just point out what those variations are. Suppose you want to choose in the secretary problem I'm talking about. Suppose you want to choose P candidates out of total n. Then how do you go about doing it? See, suppose if P was 2, meaning you needed to choose 2 candidates, then you need to have a way of knowing if the current candidate you're seeing is the best so far, or is the second best so far, or is neither of them. So your state space now has to include 0, 1 and 2. But you need to be able to distinguish between these two. So this distinguishability should be something that's possible. When you have a candidate, you should know whether it is the best one or the second best one, even if that's the first candidate you're seeing. This is something you should be able to know by that point. And then you're supposed to decide at that moment who are the 2 candidates who should be chosen. So here what will happen is the actions will become more interesting. The action is either to continue or choose a candidate. But suppose you've chosen one candidate. So you saw some pool of candidates. You chose one. The game doesn't end here, it still continues. Then you see the rest of the pool and you choose one more. Choose the second candidate. Then it ends. This is where you reached what we have been calling as the stopped state. So now how you define the transition probabilities will matter. Will be the ones that get affected. Those need to be written more carefully this time. Again, if it was not p equal to 2 and if an actual p number was there, then you'll have to consider that. Here, there's one more catch. We have not said anything about what happens if nobody is chosen. So you could go till the end and choose nobody. That is something the interviewers could do. Or if there is there's a strong constraint that you have to choose. And then that's a slight variation of the problem. Now notice in this problem the variations that I'm talking about. These probabilities will be much more interesting. They will not become independent like here, because there are states s equal to 0, 1 till whatever p you've chosen. If that is the case, then if I am the second best candidate so far, I only know that I'm the second best because I know that there is a first best somewhere. Otherwise, I don't know that. So the dependence is more complicated, and putting them in this framework is a lot more work. But sure enough, it is doable. Okay. Another variation could be to make it more complicated and actually start talking about stock prices. But there, the state space would be infinite. So that's the kind of problem that we have not entered into at all. Okay. With this, I have talked about the optimal stopping problem at length. I'll now continue with the next part. I'll stop for a moment for if there are any doubts or anything. Okay, so now let's continue with another kind of an example where DP can be used to solve for the stochastic control or the MDP problem. This one is called linear quadratic system. We are again assuming that there is a time horizon. There is some dynamics. That dynamics is linear in the states. So one example of this is inventory control. This was inventory control. Inventory control where backlogging was allowed. If backlogging is not allowed, then that's a max of something. That's not linear anymore. So with backlogging, is the one that I'm talking about right now. That's one example. So here xk are the states, uk are the actions, and omega k is whatever is the source of randomness. Now the source of randomness is such that all of these wk's are independent of each other. They're independent of xk, they're independent of uk also. They're completely independent. They are such that the mean of such noise is 0, but they have some finite variance. Okay, so the second moment exists, and this ak, bk are some matrices. So the goal here is to minimize the following object. Notice the following object, similar to what we have seen so far. This is written in the language of stochastic control. We have terminal cost and we have stage-wise cost. This is the terminal cost, and this is the stage-wise cost. The terminal cost just depends on xn, the terminal state xn, and the stage-wise cost depends on xn, depends on u. And the next states would have dynamics, and hence that's where this omega will be internally. Now here you notice there are two more matrices. These two matrices have to satisfy certain properties. Those properties are, this has to be positive semi-definite. So Q has to be positive semi-definite. And RK, which is this one, has to be positive definite. Why are we saying they have to be this way? This makes sure that the optimization has some kind of constraints. Otherwise, these optimization problems will end up taking the policy or these actions and make this whole objective just minus infinity. We don't want it to go to minus infinity, and that is being restricted by keeping these matrices as semi-definite and positive semi-definite and positive definite. Okay, now another thing, why is this positive definite? Notice where exactly this is showing up. This is showing up in the term with the actions. So we basically don't want any particular action to have no appearance in the cost. Like, we don't want free actions. What are those free actions? There might be certain actions which are aligned in such a way that this object becomes 0, and that can only happen if one of the eigenvalues of R is 0. But on the other hand, if we say that this is positive definite, then that can never happen. Each action meaning each action apart from 0 itself, will bear a cost, and that's the kind of thing we want here. And that's the reason why this is positive definite and not positive semi-definite. Alright, so this is a very standard class of problems. These are called linear quadratic systems. The dynamics is linear, so this is where the linearity is present. This is linear, and the cost has dependence on x square or x transpose x and u transpose u, which is why this is where the quadratic nature of the problem is. Okay, so now let's go further and discuss this problem in some more detail. So in this problem, if we apply dp, what we would have to do is, we will say that at the terminal cost, this is Jn of xn. We'll go one step behind, and at the previous step, we'll look at the stage-wise cost and Jn of xn, or rather, in this case, because we're at time n minus 1, so we are looking at xn, and xn is equal to this, which is what we are getting from the dynamics. Okay, so now we could write this out more carefully and see what this means. So let's do this as much as we can as per whatever time permits us. If time does not permit, then we'll think of another way. I'll just briefly talk about what happens in these problems, nothing else. Okay, so this is a minimization of un minus 1 . Notice there is no expectation for on this part. This is the current action. This is the current state information. This is the current action information. All of the randomness is here in this omega. So we could just move this expectation directly onto that part. Okay, so the expectation is on Jn of this object. And see, what is Jn of something? Jn of something is this quadratic term with qk showing up. So let's rewrite this. Okay, I'm going to do some manipulations. Transpose of this object, qn minus 1, and the same object back. This is what we have. Okay, we could look at the terms inside here much more carefully. These terms can be broken down, and we could say that this is, okay, let me copy this much. This term has no dependence on omega, so this doesn't need to be within the expectation, and hence I can write this as follows. We do have two other terms. This is one of them. And there is this term, omega n minus 1, qn minus 1, and omega n minus 1. Um, Notice this term. These are just certain constants. Remember, the expectation is with respect to omega n minus 1. This one is also with respect to omega n minus 1, or whatever is the probability of omega n minus 1, whatever that is. There's also randomness. These things are just constants, right? That means this particular term, okay, let me just copy all of this again and rewrite it. That's better. The expectation can directly go to the component where it matters. And what did we say about the mean of the noise? We said that the mean of the noise is 0. So this term does not exist, because that's how we've taken the mean to be. If we wanted, we could have kept the mean, it's fine. But for the time being, for the problem that we are currently solving, let's say that the mean is 0 and we're removing that term. Now, notice what else has happened. Now, the terms that have dependence on u are these, and from here. Okay, yeah, this one is gone. This term is all gone. This has no dependence on u. This has no dependence on u. So next thing is just to take the derivative and find out what we get from there. So let's do that. So differentiate this with respect to u n minus 1 and equate to 0. So if we do that, nothing from here, we get something from here. We get r n minus 1 along with that. We get terms from here. So let me just write it out and then you can verify if I've written it correctly or not. B n minus 1 transpose Q n minus 1 B n minus 1 U n minus 1. Okay, this is one thing that you get, plus and since there are squares, so this is u transpose u, so you'll get a factor of 2 here, and this could have been written by interchanging the transpose from here to here, so that gives you 2 terms, and this is equal to 0. So ultimately what you've gotten, and let me rewrite this more carefully, is something negative inverse of that, and you could rewrite this term and you could say that this is b n minus 1 transpose a n minus 1 x n minus 1, just interchanging the transpose, because both of them are representing the same object. Whatever this is doesn't matter. Let me just call it some l n minus 1. This is the part that matters. So what happened? My u depends on this. L is this object. Notice in this policy, this is the optimal policy, right? The optimal policy for n minus 1 step. It depends only on xn minus 1. It has no dependence on omega. Omega is not showing up. Omega is there in the optimal cost. It'll be there in the optimal cost, but it's not showing up here. We could have kept some dependence here, as in we could have taken the mean of the noise, and with just that mean we would have gotten some dependence from here. But sorry, the noise directly doesn't come up. Only the first moment of noise is all that's important, and that's the only thing that has some bearing to the optimal policy. Now notice, if you continue this process, okay, right, before you continue the process, so here J, this is the part that I'm going to just copy from the lectures. I will not talk about it more than this. For this particular this object L, okay, they've taken the negative inside, so this object L is called as the Kalman gain. And now you could write down the optimal cost, which is substitute this back in the equation over here. Once you do that, you're basically replacing the UNs with whatever LXN, appropriate LN minus 1, XN minus 1. But this is one term that will just stay. This will not go away. This can't be simplified. All the other terms will just be terms that depend on X. So what you will have is going to be an object like this. X transpose, some terms, and X again, and this extra term. This extra term has the variance of noise with respect to some Q. Okay, now this object, well, when you write it in terms of a general T with everything included, it has a name. I'll come to that. Another thing that you can check is that all of these, if you look carefully, will give you a positive semi-definite matrix. Why will that happen? Here you have a positive definite matrix. Here you have a positive semi-definite matrix. What you are taking, this object is still going to stay a positive semi-definite matrix. The sum of these two will at least be invertible. And with this invertible matrix, you have basically made it symmetric. And this will still be positive semi-definite. So you next have a sum of those two, and that stays semi-definite. So you can argue that this is a positive semi-definite matrix. You can go through the argument again if you wish. Similarly, here this invertibility is possible because this is positive definite and this is positive semi-definite. If this was also positive semi-definite, we would not be able to guarantee invertibility. Meaning one of it could have been possible to get free use, optimal free use, and that's not something we wanted, so this is what came in. Okay. Asha, now if this process is repeated for all time steps, what you get is the following. You can try doing the whole process again. We started out with a convex function, and we still have a convex function because see what we have is, this is positive semi-definite, this is positive semi-definite. So whatever this is, it's still a convex function. In fact, it's clearly quadratic in X. So the quadratic nature is preserved, convexity is preserved. This is, doesn't matter, this is just noise, some variance coming from noise with a Q, and Q we know is positive semi-definite. So this is okay. This is something, if you continue for other time steps also, you will get some appropriate L, the Kalman gain, and the appropriate K's. They have certain form. You can check that these forms are written appropriately. Then this object, the KT, this is called Riccati equation. And once you've gone through the whole process, the last time step would be the following. You will get x0 transpose k0 xt, and this k0 will be coming from this. So it will have back dependencies of all of these matrices and whatever their interactions are. See, kt depends on kt plus 1. That's what I mean by back tracing all of that. And all of these variances. Okay, so what is happening here is this has a closed form solution. You can try it out, you can check for yourself if you wish. I have shown it for what happens at time step t equal to n minus 1. I have shown it in full detail. Exact same thing needs to happen for every time step. It just needs to be done a bit more carefully, so you would see exactly what these two would look like, the LT and the KT. KT will have to depend on the previous KT plus 1. Okay, so notice the main crux of what we learn from here. Each UT depends on XT and it has no dependence on the noise. The only thing that matters for the policy or for the decision, the thing that could possibly matter is the mean of the noise that is in LT. That's it. Nothing else. The actual probability distribution does not matter. One thing that does show up in the optimal value that you're trying to minimize is the covariance of that noise. Other moments do not show up anywhere. So what this tells you is, if suppose you took the main noisy problem, this is your original noisy problem, the linear quadratic problem with noise, you replace the noise by just its mean. Okay, if noise is replaced by just the mean, then you have reduced the problem to a deterministic problem. There is no source of randomness anymore. So now solve this deterministic problem. Find the optimal policy from here. Okay, I'm not telling you to find the optimal value. Optimal cost is not something that we'll get from here. Optimal cost, we'll have to actually do it a bit more properly. This is what is needed. But this can be handled. This is just the second moment with respect to some k. Anyway, we need to know what these KTs and LTs are for that particular problem. Okay, find the optimal policy. What this example is telling you, what this whole part is telling you is, whatever is the optimal policy here will also be the optimal policy for your noisy problem. The point is, whatever LT you get here, it will be the same LT even if you took a different noise with just that the mean was same. So now the mean of the noise is the central point based on which you can classify different problems and then just solve one of them and you get the policy for all of them. And this principle, this is something that happens in LQ regulators, LQ problem, is called the certainty equivalence principle. Now, what do I mean by this? Take the mean of the noise. I'll just go back one step and show you what I mean. If I do not cancel out this term, this would be some real number, right? It's the expectation, it's the mean. This mean will show up in LT. How will it show up in LT? So let me just do that part. So now I'm taking the case where the mean is not 0. Okay, if the mean is not 0, that means this will exist. Let me say the mean is some alpha. Okay, some alpha, I don't know what it is. Let's say that's the problem. The mean shifts with every time step. Let there be some shift, but it's just some number, some sequence is what we're getting here. Okay, then this was the problem we were solving, right? This was jn minus 1 of xn minus 1. Then this term does not become 0. So okay, no problem. So what we do here is we repeat what we did before. So we differentiate with respect to un minus 1 and equate it to 0, equate the above equation to 0. So if we do that, just the same as before, so I'll get the following terms. I'll just write down the terms. I'll get Rn minus 1 un minus 1 plus an minus 1 xn minus 1 transpose qn minus 1 un minus 1. This u went away. Okay, there is one more term. This is the term that's coming because of this. This is bn minus 1 transpose. It needs to be written more carefully. So that is alpha n minus 1 q n minus 1 b n minus 1. Okay, and there is one last term that is because of this component, which is bn minus 1 transpose qn minus 1 bn minus 1 un minus 1, and this all needs to be equated to 0. So what exactly has changed here? Let's rewrite this. This is I'm just clubbing the terms that have un minus 1 with it, and the terms that don't have it, I'm taking it to the other side. Okay, there's a factor of 2 that I forgot to write here, right? That's why it looks so odd. Yeah, okay, that factor will just get cancelled. Why will it get cancelled? Here you'll get a factor of 2 eax. Yeah, you would get a factor of 2 here. From splitting this, then here you're getting a factor of 2 from here. Here you'll get a factor of 2 because of differentiation. Okay, so all of these 2's will go away. Then this becomes Now hold on, did I make a mistake in how I've written it? Okay, there's supposed to be a bn minus 1 here. Okay, so this is the same as before, plus there is this offset factor. This offset factor has no dependence on x or anything. This is alpha and 1 q and minus 1. Okay, and if you want to write what is un minus 1, that is just the inverse of this. So if you compare it with the previous version, what we had, this is minus L this is one part, and along with that we have the following. Times q and minus 1. And there is this alpha. This is anyways more like a scalar, so it's fine. So I could say, okay, this is some beta of n minus 1, and this whole thing. Then what I have is this is some kind of a offset that got introduced. In the previous case, this was 0 for all time steps. That's why this didn't exist. Now, the presence of this does affect the cost also. So if you want, you'll have to go through the cost carefully to talk about what is the optimal cost. Because this term not being 0 will affect the cost. So there will be some additional terms. But the point that is important here is it's only the first moment of noise that is showing up in the policy. Okay, and that is nothing but an offset, that's it. That offset is not something that depends on x. And is a scalar, it's not a random quantity anymore. So what did we learn from here? Any noise that has this type of a mean will give us exactly this policy if we are in the linear quadratic problem regime. This would be the optimal policy. Similarly, we could go further. This is something that you'll have to do carefully, but you could define what will happen at time step t. So there will again be some lt of xt and some other terms or term. These terms will have dependencies on alpha t. And you can also have j star of t at some xt. It'll be the core terms. The core terms are these ones: xt transpose kt, the Riccati equation, xt plus the sum of omega t qt, not qt, sorry, kt omega, plus possibly other terms that are due to this alpha t. Whatever time steps we have considered. So maybe if we're starting from 0, so 0 till that. Okay, so what exactly happened here? What we have done is all noise with mean alpha t, so for each t, is captured in just the presence of this alpha t in the offset. So ut has the term that depends on xt and the term that depends on alpha t. There could be other terms, that's okay, but that's it. So this same policy will hold for any LQ problem with mean with noise omega, where omega t is equal to alpha t. So all of those got clubbed into just one class of problem. Okay, and this is what is referred to as uncertainty equivalence. There is a way of putting different kinds of uncertainty in one class. A lot of more interesting things happen in these LQ problems, and we'll talk about them more specifically in the upcoming lectures and the tutorials. For the time being, this is what I had planned for today, so I'll just take a quick recap of what we did. Okay, so we started by talking about or taking a recap of what is called as the DP algorithm. We know DP algorithm is a backward induction type algorithm where you start from the last time step and go recursively backwards. So you start from n, you go to n minus 1, n minus 2, and so on till you reach the last time step, the first time step, whether it's the first or the 0th, depending on how you define the problem. And then the optimization reduces to just doing this following optimization. You're just optimizing for the policy at a time interval k, and to do that you end up using whatever had happened in the previous time step. And the dynamics also shows up. This is what we have, and we applied it to two problems. One of the problems that we applied it to is called the optimal stopping problem, which can be thought of as two examples. One example could be a finance example, coming up with a strategy for when to exit from a stock or to continue, or similarly for options also. So it's a finance example. Another example which we discussed in a lot of detail is the interview panel example, or what is called as the secretary problem. In the secretary problem, the idea is that there are n candidates and one needs to be selected, but the selection happens online, as in it happens instantaneously. Either the candidate is chosen or he's not chosen. He's given an offer right then and there, and the interview ends for every candidate, the process is over, or the panel keeps looking at the number of candidates that are present. So this problem is modeled by looking at the state, and the state is defined in the following way. The state is who is the best candidate so far. Each candidate who comes, if you could possibly have a ranking of all those candidates. So each candidate who comes, you'll know whether the candidate before it was better or not. That's all the information you'll know. You can think of it like the interviewers who are taking the interview, based on the kind of questions they ask and the kind of answers they get from the interviewee, they'll be able to make a judgment of, is this the best candidate so far or not. So it's sort of mapping that into the state. They'd also be able to even rank based on the candidates that they've seen. This is the best candidate so far, this is the second best candidate so far. That's something they can do. Okay, so currently this is the scenario with best candidate so far. The problem is that the interviewers are supposed to decide whether to continue the interview process or to stop the interview process and give offer to the current candidate. If the interview has already stopped, then there is nothing more for them to do. So it just doesn't matter. You can say that the only action available at that point is to continue. The Markov chain continues on its own and they have nothing to do there. So here the problem is taken in such a way that the cost if you decide to continue, there is no cost for that. But if you decide to stop and give the offer, it depends on who the offer has gone to. So if you gave the offer to somebody who's not even the best at that time, then your reward is 0. Because the idea is to try and give the offer to the best candidate possible. So it needs to search for the best candidate without looking through all of them and then choosing. Okay, so the reward for choosing a candidate S who is best so far at time t depends on what is the probability that this is the best candidate so far. This is the best candidate overall. Now, what does this mean? We can look at an example for that. So in the example, we saw that there are a few variations that you can come up with. Suppose there are 10 candidates. We can write them in terms of their rank, or we can write them in terms of how they show up one by one. This is something nobody would technically know. This is something the interview panel will be able to figure out based on the interview that they're taking. Okay, so now the reward depends on what is the probability that whoever is the candidate they're seeing right now, is that the best candidate or not. And that just depends on T by N. Or it's like saying, if the current candidate that I'm seeing is the best candidate so far, that means the candidates I must have seen before that, what is the way of arranging those? So that is from n minus 1 candidates, choose t minus 1 candidates. Okay, and if the current one is not that, so arrange all of them in whatever order. So choose t from n. That's what you would get. That's the comparison. And that tells you what is the probability of getting that the current candidate is the best candidate so far. Is the best candidate overall, not so far. Then that turns out to be t by n. That's just dividing these two. Then something else is defined which is actually properly correlated with this, which says that the terminal cost, if you have chosen a candidate who's not the best so far, if s is equal to 0, then it's 0. What does it mean for the last candidate to be 0? Last candidate 0 means it's not the best candidate overall. That's a clear situation. If you know that the best candidate is not being chosen, then if you have not chosen anybody and you let it go until the last one, then you should not be getting any reward from the panel's perspective, right? But if the last candidate is the best so far, if it is s equal to 1, then best so far is actually the best, because only then it will be the best so far and you've reached the end of the chain. So that means you ended up taking the best candidate, and hence you should be getting the maximum reward, which is 1. Notice you'd get the best reward in this process only when t equals to n. There is no action to be taken there, so the maximum reward that you can get from this process is n minus 1 by n, or at the last time step n by n, which is 1, which is exactly what this is. So these two are correlated with each other. It's making complete sense. Okay, next thing is to look at the transition probabilities. Remember, we are looking at only this transition probability, because in the case we are looking at only the case where the action is to continue to continue looking. Then whether your current candidate is the 0th one or the first one or the best so far or not doesn't depend on the previous candidate you saw. They're not correlated with each other, at least in this scenario. When that is the case, you don't need to look at the transition probability, this one. You just have to look at what is the probability of getting a candidate that is the best so far. And the probability of getting the candidate best candidate so far is just number of arranging t versus number of arranging t plus 1. That's it. Versus the opposite, which is t by t minus t divided by t plus 1. So these are the probabilities. Okay, next step that we did is to maximize this object. In the process of maximizing, we used dp. And we wrote down what is the expected cost. We wrote down the expected cost carefully by looking at the transition probabilities, taking the expectation of jt plus 1, and we did the whole process, and we managed to simplify it to reach a set of rules. We did not prove it, but it was proven in class that this is the best policy, that up till you reach a stopping point, optimal stopping point, it's better to just continue. Once you reach the stopping point, give the offer when you find the best candidate so far. If you're not finding the best candidate so far, no matter what time it is, you should not stop. That's what the policy is, and it's a very simple policy. And we also saw that the policy is such that this optimal time depends on the number of candidates. So if you have seen roughly 37% of the candidates, that's when you should have your optimal stopping time. After that, choose the best candidate you see. Choose the next best candidate you see, and you're done. Okay, then all of this logic of DP is what we applied to problems with linear quadratic systems. We saw that in linear systems, we are minimizing a quadratic cost. In this type of a problem, the optimal action ends up being directly related to xn minus 1, or x, the current state. And this is the term that has dependencies on whatever were the matrices in the problem. This policy has no dependence on the randomness. One, obviously the randomness is not known, but randomness is showing up at every time step. It is affecting how your action is being taken, what state you're going to next. But it's not a part of your policy. This idea leads to what is called as uncertainty equivalent principle, or principle of uncertainty equivalence. It says that take a noisy problem, consider only the mean of that noise. If you're only considering the mean of the noise, it becomes a deterministic problem. Solve for the optimal policy, and whatever policy you get from here will also be the optimal policy for the noisy problem. This is something that tends to happen in LQ problems. In fact, this idea is many a times applied to even nonlinear problems, hoping that this works. So this is one of the core principles. We saw what it means to take the mean of the noise, what exactly that means and how it shows up in the optimal action. It just becomes an offset factor. Okay, so with this we have started talking about linear quadratic systems. Next we'll talk more in detail about if the noise was Gaussian, then the closed form is even nicer. And what else can we talk about from this point onwards? Okay, if you have any doubts, remember to reach out or join this call. Thank you.